All right. Good morning, everybody. So let's pick up where we left on Wednesday, and then after that, we can go have uh, 1 week off. Okay. Oh, so one thing I want to tell you, sometimes my headphones, they get muted for some reason. So if you ask me a question and I don't answer you right away, it's not that I'm ignoring you. Just send me a message through the chat, and then I can figure out if the microphone, if the headphones are muted or not. Okay, so let's do this. All right. So that was the last thing I showed you on Wednesday. So we went over the 4 different types of chemical reactions. And I showed you the combination or synthesis elimination, single displacement, and double displacement. So you must be able to recognize all the different types. Doesn't matter why they happen at this point of the course. Okay, so now let me introduce you the concept of mole. So this is sometimes a hard concept for the students to understand. So let's try to understand it. Okay, so here the idea is that we cannot manipulate a single atom or a handful of atoms. Therefore, we need a huge amount that we are able to handle. So imagine here the following analogy. If you are able to pick up 1 grain of coarse sand, that will fit on your fingerprints. But as you can see, it is really hard to manipulate just 1 grain of sand. However, if you have 1,000 grains of coarse sand, oh, look at that. Now it fits on the palm of your hand. And if you go even further and have 1 million grains of coarse sand, now look at that. It's a huge cube. We can hold this cube. We can manipulate this cube. We can put on a scale and do things with that. It's the same idea with atoms. We humans are not capable of manipulating individual atoms or molecules in a regular lab. Therefore, we always need to work with a massive amount of them. And this massive amount, it is 6.022 times 10 to the 23rd. And it is called Avogadro's number. And it was chosen to represent this massive amount of stuff. Okay, so every time we have 6.022 times 10 to the 23rd entities of stuff, we call this huge amount 1 mole. Moreover, the symbol for mole is mole without the E at the end. Okay, so when you are writing in a regular text, you can write M-O-L-E. However, when you are expressing the result at the end of the calculation, you have to use M-O-L. And that's the idea behind the mole. It's just a huge amount of stuff, and the number that represents this huge amount is 6.022 times 10 to the 23rd, and it is called Avogadro's number. Thus, you can have 1 mole of anything, 1 mole of eggs, 1 mole of atoms, 1 mole of dollars, or 1 mole of shoes. In all those cases, it means you have 6.022 times 10 to the 23rd entities. Okay, so I want you to see the relationship between the Avogadro's number and mole as a simple conversion factor. And we know how to deal with conversion factors. All right, let me switch to my other screen here really quick. Okay, so the best thing to do in this part of chapter 3 is to practice with lots of exercises. So I will do with you some examples here. Obviously, I cannot cover all the cases, so I will give you the basics, and from there you have to take on your own, okay? So again, every time I'm talking about 1 mole of anything, it means 6.022 times 10 to the 23rd of whatever I'm talking about. So imagine this as a conversion factor. Okay, so let's try to tackle this example here. For an adult, the little dose of arsenic is around 1.33 times 10 to the minus 3 mole of atoms of arsenic. How many atoms of arsenic are in the little dose? The Avogadro's number is 6.02 times 10 to the 23rd. Okay, so first thing here is to identify what are we talking about, okay? So what is the thing that we are talking about? So if you go back to the question, it says 1.33 times 10 to the minus 3 mole of atoms, okay? So we are talking about mole of atoms. And I'm going to use this conversion factor over here. So let me rewrite it right here. So 1 mole of, in this case, we are going to fill this gap with atoms, because that's the thing we are dealing with. See, going to simply put atoms in the gap, and this is equals to 6.022 times 10 to the 23rd. And this next gap here is going to be filled with the same thing that I put in the first gap, which is atoms. And this is going to be our conversion factor. Okay, so that's the relationship between mole of atoms and the amount of atoms that we have. And we know how to deal with conversion factors. Okay, so the question here is for 1.33 times 10 to the minus 3 mole of atoms, how many atoms do we have? So now let's set up our conversion. So remember that I showed you. So we are going to label the first column as everything that has moles, and the second column, everything that is the amount of atoms, because that's what we are dealing in this problem. We know that 1 mole corresponds to 6.022 times 10 to the 23rd atoms, because that came from our conversion factor. And remember here, the trick is to divide those amounts by the numbers you have and the numbers you want to find. We know that 1.33 times 10 to the minus 3 mole from the question, and the question is asking us to find the amount of atoms in 1.33 times 10 to the minus 3 mole. Okay, so the first column, you put everything that is in mole. The second column, everything that represents the number of atoms. From the conversion factor, 1 mole of atoms equals to 6.022 times 10 to the 23rd atoms. That's going to fill up the second line. And then, sorry, the first line. And then the second line, you always have one information and it's looking for the second one. This is a simple proportion. So let's do a cross multiplication here. So this will be x, x times 1 mole equals to 6.022 times 10 to the 23rd atoms times 1.33 times 10 to the minus 3 mole. Okay, so we don't need to do that, but I'm just going to show you. So we have to isolate x, therefore 1 is going to move to the other side doing the opposite operation. X is going to be equal to 6.022 times 10 to the 23rd atoms times 1.33 times 10 to the minus 3 mole over 1 mole. You can cancel mole with mole. What's left here? So now I'm going to organize numbers and powers. So just to make it a little bit more simple, I'm going to write 6.022 times 1.33, and then I will write everything that has powers. Okay, 10 to the 23rd times 10 to the minus 3. Okay, so now that you got all the way to this point, it would be a shame that you mess up the math. So x is going to be equals to 8.01 times remember that when you have a multiplication of powers, you are going to keep the base, which is 10, and add the exponents. Okay, 23 plus, watch out for the sign here, minus 3. 23 plus minus 3, that is 20. Therefore, our answer will be 8.01 times 10 to the 20, and the unit that was left here is atoms. Okay, that's our final answer. Just let's put in the box, and then everybody knows where the answer is. Another thing here that you must pay attention is about the number of sig figures. Remember that the conversion factor will never count for the number of sig figures because it's something we are sure about. Therefore, the determining factor for the sig figs is this number over here. And for this number, we have 3 sig figures. And that's why we are representing the result with 3 sig figs. All right. Okay, so those kind of problems just follow the first initial conversion line here. Remember to fill the gaps with whatever the exercise is dealing with. And whatever you put in the first gap, that's going to be the same thing in the second gap. And that will give you the conversion factor. And from there, it's just simple proportion, and be careful with the math, okay? So it's really easy to get lost or make a mistake when you are dealing with powers. Pay attention to the number of sig figs, and if you follow all of that, you should not have too many problems. So I would like to solve one more example, and then we can move on from here. Okay, so now let's see what the question is asking us. If a sample has 3.5 times 10 to the 5 atoms of sodium, so attention here. Now we are dealing with atoms of sodium. And that's what's going to fill the gaps here. If a sample has 3.5 times 10 to the 5 atoms of sodium, what is the number of moles of atoms of sodium in this sample? Avogadro's number is equals to 6.02 times 10 to the 23. Okay, so first thing, let's build our conversion factor. So we are going to use this line over here. 1 mole of, we are going to fill the gap with atoms of sodium because that's the thing that the exercise is dealing with. Atoms of sodium. So I'm going to represent sodium here by the symbol Na, is equal to 6.022 times 10 to the 23rd. Whatever you use to fill the first gap, you are going to use for the second gap. Therefore, we are going to fill it up with atoms of sodium. And that is our conversion factor. So pay attention now. Now the question is giving you the amount of atoms and asking you the number of moles. Okay? So that has to be clear. Question is asking you, is giving you the number of atoms and asking you the number of moles. Okay? What is the number of moles? So let's set up our proportion. So I'm going to do exactly the same thing that I did before. First column is going to be mole. And the second column here is going to have atoms. The first line, we are always going to write what we have for the conversion factor. So we know that 1 mole of atoms is equivalent to 6.022 times 10 to the 23rd atoms. Okay, so let me write this in another way. I'm going to just write 1 mole here to make it simpler. So again, the first line always comes from the conversion factor. Now we are going to divide both sides. The exercise is giving us the number of atoms. Attention here. Therefore, this value will go in the atoms column. 3.5 times 10 to the 5 atoms. And it's asking us what's the number of moles. So that's what we are looking for. The number of moles. Okay, so from here is just a simple proportion. Let's do a cross multiplication. So it's going to be x times 6.022 times 10 to the 23rd atoms equal to 1 mole times 3.5 times 10 to the 5th atoms. Okay, if you got all the way to this step, now it's just math. So be very careful with the powers here. So we need to isolate x. Therefore, we are going to move 6.022 times 10 to the 23rd to the other side, doing the opposite operation, which is division. X is going to be 1 mole times 3.5 times 10 to the 5 atoms divided by 6.022 times 10 to the 23rd atoms. All right, atoms on top and atoms on bottom, we may cancel. Therefore, what's left here is that x is going to be 3.5 divided by 6.022, oops, times 10 to the 5 times 10 to the 23rd. Okay, so according to my math, therefore, let's organize this a little better. Therefore, x 3.5 divided by 6.022, that's going to yield 0.58. Attention here with the power. So now we have a division of powers. So we are going to keep the base, keep the sign of the power on top, and subtract the power at the bottom. Very careful when you have the division. That's going to give us 10 to the minus 18. The unit that was left here is mole. And that is our final answer. But inside the box, and everybody knows where it is. Okay, so pay attention here to the number of sig figs. Conversion factor never counts for the sig figs. Our limiting here is 3.5, which is 2 sig figs. Therefore, we have to have 2 sig figs here at the end. All right, guys, so nobody will ace this concept at first. That will require some work, trial, fail, go back again, try again, and then you will master the concept. All right. So now let me go back to my PowerPoint. Okay, so now I would like to show you the concept of molar mass, or also called atomic molar mass. The atomic molar mass is simply the mass of 1 mole of atoms, or 6.022 times 10 to the 23rd atoms. The unit for atomic molar mass is grams per mole, or you can write in a more fancy way, grams space mole to the -1, okay? So where do you find the atomic molar masses for the elements? The answer is very simple. It is in the periodic table. So here at the bottom of each element, we have the average atomic molar mass for all the elements, okay? So this number here is going to correspond to the atomic molar mass for any individual element, and the unit that we are going to use is grams per mole. For example, the molar mass for potassium, right here, is 39.098 or 39.10 grams per mole. The meaning of that is that 1 mole of atoms of potassium weighs 39.098 grams. And that's equivalent to 6.02 times 10 to the 23rd atoms of potassium. Okay, so now what I'm doing with the atomic molar mass is adding one more thing to our conversion factor. Okay, so we started with the relation between mole of atoms and number of atoms. Now we are going to add the weight of the atoms to our conversions. Okay, so remember that the relationship now it's a little bit more complex. The molar mass of a given element is the mass of 1 mole of atoms of this element and contains 6.022 times 10 to the 23rd atoms. So let me show you how that works with an example. Consider a sample that has 1 gram of potassium. Okay, so again, you can go back to the periodic table and find the atomic molar mass for any element. And in the case of potassium, we are talking about 39.1. So that's where I'm extracting the molar mass for potassium. Okay, so the first question, how many moles of potassium are in this sample? And then how many atoms of potassium are in this sample? Okay, so the first thing here is to set up our conversion factor. So let me show you how to do that. And then let's think for this exercise for a couple minutes, and then I will solve it with you. So let me switch again to the iPad. Okay, so see here I always will give you this information. Okay, so that's the atomic molar mass for potassium. So now let me write the conversion factor all the way up here. So I'm going to start with the atomic molar mass. So in this case, potassium is 39.098 grams. Every time we have the atomic molar mass, that is going to be equivalent to 1 mole of, in this case, potassium, okay? 1 mole of atoms of potassium, if you want to be more precise. So let's do that. 1 mole of atoms of potassium. And every time you have 1 mole of anything, we immediately have to correlate that to 6.022 times 10 to the 23rd. If we are talking about atoms of potassium, we have to fill this gap with atoms of potassium. Okay? Again, from the atomic molar mass that we extract from the periodic table, I know that this corresponds to 1 mole of atoms, and that corresponds to 6.022 times 10 to the 23rd atoms. See now that our conversion factor got a little more complex. So with that, we can use any part of the conversion factor according to what the question is asking us, okay? So keep in mind that this first part of the conversion factor relates to mass. The second part relates to mole. And the third part relates to atoms. Okay, from the question, we know that the mass that we are dealing with is 1 gram. The first question asks us how many moles, okay? So that rings a bell. We have mass and we want to know the number of moles. Therefore, I'm going to use the first 2 parts of the conversion factor because that relates mass with mole. Okay, that's the trick here. So let's set up our proportion. So I'm going to write in the first column everything that corresponds to mass. And in the second column, everything that relates to mole. The first line always comes from the conversion factor. We know that 39.098 grams of potassium is equivalent to 1 mole of potassium. The second line you always going to have one number, and your goal is to find out the second one. So let's divide from the exercise. We know the mass, so therefore that has to fit in the mass column. And we want to know the number of moles, X. Once the proportion is set up, now it's just a simple cross multiplication. So we are going to end up with X times 39.098 grams equal to 1 gram times 1 mole. Let's isolate X. Therefore, we are going to move 39.098 to the other side, and we are going to do the opposite operation. We will end up with 1 gram times 1 mole divided by 39.098 grams. Let's see what we can cancel unit-wise here. Grams on top and grams on bottom. That goes away. Therefore, X is going to be equal to 1 over 39.098. And according to my numbers here, this is 0.026, and the unit is mole. If you wanna write a better answer, you can transform that in scientific notation, and that's going to be 2.6 times 10 to the minus 2 mole. Put it inside the box, and everybody will know where the answer is.
Professor, I've got a question.
Yes.
So it's 2.6. It's only using two significant figures because the question originally asks for 1 gram, and it's 1.0. So and that's two significant figures. So that's okay. Thank you.
Yes, yes. So remember, you never count the conversion factor for the sig figs because this is something we are sure that we know. So it's considered exact. So you don't have any questions about the numbers there.
Okay. And we don't use the molar mass of potassium because we know that's an exact number and we know that value.
Yes, yes, yes.
Okay.
This is considered an exact number, so you don't have to consider that for your sig figs. Yes, thank you for your answer, for your, sorry, your question.
Thank you.
Yes. Okay, so if you were able to solve that, that's great. We are heading in the right direction. If not, don't get discouraged, okay? So let's work hard on that, and I'm sure we will master it. So let's now solve the second part of the question. Okay, so pay attention to the second part now, because now the question is asking you how many atoms, okay? So now we are going to use uh, the factors that correlate mass with atoms, okay? Or one thing that you can also do, because you know the number of mole, is to correlate mole with atoms, okay? I prefer to use mass and atoms And the reason for that is if you use mole with atoms, you depend on your answer. If you messed up your answer, you will mess up the second part of the question. So always use everything that the exercise gives you, because that will not require some previous calculation when it is possible. Okay, so that's what I'm going to do here, because it is possible and we will play safe in the beginning. Okay, so I will not have time to finish up, but I will set up everything here. So now I'm going to use the part of the conversion factor that correlates mass with number of atoms, okay? So my first column is going to be mass, and my second column, atoms. Look at the conversion factor, 39.098 grams of potassium. Just ignore the middle of the conversion factor because it's all equal. And let's jump all the way to the last part of the conversion factor. And this is going to be equivalent to 6.022 times 10 to the 23rd atoms. Okay, the first line always comes from the conversion factor. The second line, you will extract one information from the question, and there is always something that you are looking for. So the question gave us the mass of potassium and is asking us the number of atoms. So I'm going to put X over there. Okay, so we are almost short. We are very short on time here. I will not solve step by step with you, but I will give you the answer. So try to do by yourself, and you gotta get 0.15 times 10 to the 23rd atoms. Okay, that is the answer to the question. And with that, I will finish at this point. That's more than enough for today. So next week, we don't have classes. So take a break, recharge your energies, enjoy your family and friends, enjoy your time, because time cannot go back. If you didn't enjoy, you will lose the opportunity, okay? So enjoy life, okay? So get some rest, and I will see you after spring break. Okay?
Thanks, George.
All right,
Bye-bye.
profs. Have a good one.
Thank you.
Thank
Bye-bye.
you. Thank you.
Thanks, Professor. Have a good spring break. I've actually got a question about this answer real fast, if you've got a second.
Yes, of course.
So I did the math real fast, and what I got was 1.5 times 10 to the 22nd power.
Yes, that's
so
the same thing.
Yeah, it's the same thing. Is it okay to have it in both, or do you
Whatever.
prefer what form or over the other?
I don't care.
Okay,
Yes.
sounds good. Thank you very much, and have a good break.
You too. Bye-bye.
Bye.